We've already looked at graphing position versus time, so in this video I'm going to show you graphs plotting velocity versus time. So on the y-axis we will have v for velocity, and again we're usually measuring that in meters per second, and then t for time, which we are measuring in seconds. So you may be asked to plot a graph where something is stopped. In the position versus time graph, we saw, a flat line like this because the position was the same at every moment and the slope was zero, meaning that the velocity was zero. When you plot a graph for velocity versus time for something is stopped, this is going to be the 0 point. So it's going to look just like this. It'll be at 0 the entire time. So this is for something that's not moving at all, right? Then we talked about the fact that velocity could be forwards or backwards. So if you have some constant positive velocity, that means we're going to have some line that is going to be flat, right? Because it's not accelerating, it has the same velocity every unit time. And so it would be some positive value up here, okay? So this would be a constant positive or forward direction velocity, right? Now, if we wanted to plot one moving backwards or going in the negative direction, then we'll have to extend our graph a little bit here. So this is where 0 is, and we'd have plus here and minus here. And so down here on the bottom, we would have some negative but constant velocity. So this is a constant negative velocity. And in none of these cases do we have an acceleration. So there is no acceleration in any of these graphs here. And let's sort of look at, how we can tell that. Obviously, we know we're going at constant speed, and I said that, so we know there's no acceleration, but let's look at it in terms of the math. So we have acceleration is equal to change in velocity, or velocity over time. So in this case, this would be my rise, and this would be my run. So a position or a velocity versus time graph, the slope of a velocity versus time graph is acceleration. So in all of these cases, the slope is 0, so the acceleration would be 0. All right, now let's look at some examples where we actually are seeing some acceleration. All right, so if we were speeding up in the positive direction, we'd have some constant positive acceleration, right? So the slope would have to be positive. So in this case, we're going to have a line that looks something like this, right? So this is a positive constant acceleration. And if we wanted to go the other way, this would be a negative acceleration. All right. Now, we won't often look at examples where we don't have a constant acceleration. If we did, these graphs would then look curved because then the instantaneous acceleration would be changing our slope. But we don't typically go that far when we look at a changing acceleration. So for now, we're just going to keep it to problems where we have a constant acceleration. Now, there's one more thing that I want to point out to you about velocity versus time graphs, which is really important. And if you've taken calculus, you may have learned about this, right? So if I have velocity over time, right, and let's say I am going a constant velocity, I'm going to put some numbers in here, like 10 meters per second, and let's say I'm doing that for 5 seconds, right? So my graph would look like this, going across at 10 meters per second for 5 seconds. Is there a way from this graph that I could actually figure out how far I was from where I originally started? So my displacement, right? So let's look at these mathematically, how they relate. So remember that velocity is equal to displacement over time. So if I were to multiply, if I were to solve this equation for displacement, I could say velocity times time will give me displacement. And if we look at a graph, I can see that here I have velocity on one side and I have time on the other side, right? Well, I guess it's time this way and velocity this way. So if I were to multiply velocity by time, it would be equivalent to the area under the curve. So the displacement can be calculated by taking the area under the curve for a velocity versus time graph. So displacement is equal to the area under curve for a velocity versus time. Right? So in this case, it's really simple. I just have a rectangle, so it would be 10 times 5. So the displacement in this case would be equal to 50 meters. Now, this is algebra-based physics, so all of the area under the curve problems won't technically be curves. They'll always be either rectangles like this, or maybe triangles if we were up here looking at this, so we'd have to be able to figure out the area of that, so base times height divided by 2. But you will be asked to calculate for different instances. However, if you have taken calculus, you may have learned how to calculate the area under the curve, but if not, that is not necessarily for this class. So we will go and we will be looking at position versus time graphs and velocity versus time graphs that are a lot more detailed and complicated than this, but this should get you started with just the basics.